Hi, we are Group45. Our presentation topic is about post-quantum cryptography. We will first introduce why it's so important, and after that, we will introduce four main candidate methods in this area for now. Nowadays, attackers currently have to rely on increasingly faster computer systems and increasingly superior cryptography algorithms to improve their efficiency of their attacks, which may not be the case in the future. With the development of quantum computing technology, most public key cryptography algorithms such as RSA, elliptic curve cryptography, and Dave Hoffman are gradually become unreliable, since the hard mathematical problems underlying these algorithms can be solved by quantum computers and their quantum computing algorithms. The well-known example is IBM's quantum computer and Schwar's quantum computing algorithms. They were created to solve the problem of large prime factorization and discrete logarithm problems. In addition to this, although it's possible for most symmetric cryptographic algorithms to coexist with quantum computers by adjusting their parameters, the efficiency of the cryptographic algorithms is also challenging modern symmetric cryptographic algorithms. The growing needs for new computing platforms such as cloud computing, mobile payments, and Internet of Things is a requirement to develop new, secure, and easy-to-implement cryptographic algorithms is therefore becoming increasingly important with the rise of quantum computing technology. This project will focus on four main methods which are hash-based, code-based, multivariate-based, and lattice-based. At the end, we will also introduce the application about these methods. Currently, algorithms like RSA are widely used in identification and authentication protocols, but quantum can cause them to be neutralized. Hash-based signature algorithms can resist quantum computer attacks. The idea is that the algorithm is not secure if two documents can be signed using the same digital signature, and if there is a collision-resist hash function, it can make sure that one document only signed with one unique signature. Therefore, it is considered as an alternative digital signature towards post-quantum cryptography. One example here is a stateless hash-based signature called Sphinx. It combines multiple Merkle trees proposed by Rafael Merkle and one-time signatures. It eliminates the states for a different purpose to avoid load balancing, multi-threading problems, and etc. The Sphinx 256 is often used version of Sphinx. It roughly takes 52 million cycles on the 4th-gen Intel CPU on signing, which took more than 200 signs per second, and 1.5 million cycles for verification and 3.3 million cycles for key generation. Hash-based digital signature is currently one of the most promising alternatives to traditional digital signatures.
Next, I will introduce a code-based algorithm. Code-based algorithms are mainly used to construct encryption algorithms in order to calculate and rectify random errors. This technique uses error-correcting codes. A well-known code-based encryption algorithm is McAlice. McAlice uses a random binary irreducible Cooper code as a private key, and the public key is a general linear code after transforming the private key. The primary issue with this approach is that the public key size is too big. Numerous ideas have been put forth by researchers, but most of them have been proven by other researchers to be infeasible. Only the original McAlice is still useful for future study. Next, take Alice and Bob as an example. Alice wants to send a message to Bob. Bob chooses arbitrary Cooper polynomial and then compute matrix J of the Cooper code. Bob randomly chooses an invertible matrix S and the permutation matrix P. Then Bob computes J prime, which is his encoding matrix. The private key consists of the polynomial, the original matrix G, along with matrices S and P and G prime. After Alice has public key of Bob, she generates random binary vector E. so Alice can encode her message and send her cipher text. Bob receives Alice's code word and uses his permutation matrix to compute this, and then he can decode Y prime into the message by finding E prime. Once this is done, Bob can calculate this and then recover the original message. In addition to code-based and hash-based crypto systems, multivariate-based cryptography is one of its main candidates. The main applications of multivariate-based algorithms are key exchange, encryption, and digital signatures. A representative algorithm called HFEV- is still operational today. The complexity of solving nonlinear equations or multivariable quadratic polynomial problems determines the security of multivariable cryptography. The multivariable algorithm, which has a faster processing speed than the traditional cryptographic algorithm, based on number serial but a larger public key size, is best suited for application scenarios where frequent public key transmission is not necessary.
Just a few months ago, NIST published a status report on the third round of the NIST post-quantum cryptography standardization process, identifying 4 algorithms that are ready for standardization. Among these 4, Crystals Kyber, Crystals Dilithium, and Falcon are all lattice-based algorithms. So let's start by understanding what a lattice is. A lattice L is a linear combination of integer coefficients of a set of linearly independent non-zero vectors determined on a linear space R. And this set of linearly independent non-zero vectors is B. B is called a set of bases of the lattice L. For example, a two-dimensional coordinate system can be considered as a lattice. Point 11 and point 21 can be considered as a set of lattice spaces of a two-dimensional integer lattice. We know that to guarantee the security of a cipher, it is necessary to ensure that the underlying mathematical problem that implements it is difficult. There are quite a few classical hard problems in lattice, such as shortest vector problem, closest vector problem. Among the practical applications of cryptography, the difficult problems on which lattice cryptographic algorithms are based are more often used in learning with arrows problem. The left figure is a non-homogeneous linear equations. Given a random matrix A and a vector B, it is feasible to introduce an unknown S. And introducing arrows on the left figure will be an LWE problem as shown on the right side. Given a random matrix A and a vector B, it is difficult for us to derive the values of S and E from these. The LWE problem can be reduced to a difficult problem on a lattice. Solving the LWE problem is no less difficult than solving a difficult problem on a lattice. Next is the application scenario. As you can see from NIST, it is most concerned with some basic and widely used cryptographic algorithms, public encryption, key exchange, and digital signatures. These post-quantum cryptographic algorithms, which have been identified for standardization, can directly replace existing cryptographic algorithms. Like those existing cryptographic algorithms, post-quantum cryptographic algorithms can be used in a number of high-level protocols and applications, including HTTPS, digital certificates, digital concurrencies, desktop and mobile operating systems. In addition, post-quantum cipher can perform many functions that cannot be achieved by traditional cipher. For example, homomorphic encryption. Data is stored in a database in an unencrypted state, and we can perform data processing. If these data are encrypted, they cannot be calculated. Then the database needs to decrypt the data first. However, this would be a threat to the user's data privacy. In contrast, the homomorphic encryption algorithm can process user data without decryption, so that the security of data is greatly ensured. This is all we have reported. Thanks for watching.